System specification. In this video, we are going to see about system specification. The system specification describes the function of a computer-based system and the constraints that will govern its development. The system specification review evaluates the correctness of the definition contained in the system specification in order to ensure that the scope of the project has been correctly delineated, functions, performances, and interfaces have been properly defined, analysis of development risk justify the system, the developer and the customer have the same perception for the system. A system requirement specification is normally produced in response to a user requirement specification or other expression of requirements and is then used as a basis for system design. The system requirements specification typically differs from the expression of requirements in both scope and precision. Later may cover both the envisaged system and the environment in which it will operate, but may leave many broad concepts unrefined. Traditionally, system requirement specification took the form of natural language documents. However, both the need for precision and problems with the increasing size of specification documents have led to the development of more formal notations. These are capable of being mathematically manipulated so as to show that the system as designed and implemented actually meets the specification. A system requirement specification may also be used in contract negotiations during and after the purchase of the system, which must meet the specifications that the contractor has agreed to accept. This is especially important where the purchaser sets out the requirements in terms of a range of functions and performance levels that the contractor commits to supplying and meeting, rather than as inventory of components, that is hardware and software, that the contractor undertakes to supply. Software Requirement Specification (SRS). In this video, we are going to see about Software Requirement Specification (SRS). After the analyst has gathered all the required information regarding the software to be developed and has removed all incompleteness, inconsistencies and anomalies from the specification, he or she starts to systematically organize the requirements in the form of an SRS document. The SRS document usually contains all the user's requirements in a structured through an informal form. Users of SRS documents. Usually, a large number of different people need the SRS document for very different purposes. Some of the important categories of users of the SRS document and their needs for use are as follows: users, customers, and marketing personnel. These stakeholders need to refer to the SRS documents to ensure that the system as described in the document will meet their needs. Software developers. The software developers refer to the SRS document to make sure that they are developing exactly what is required by the customers. Test engineers. The test engineers use the SRS documents to understand the functionalities and based on this, write the test cases to validate its working. User documentation writers. The user documentation writers need to read the SRS documents to ensure that they understand the features of the product well enough to be able to write the user's manual. Project managers. The project manager referred to the SRS document to ensure that they can estimate the cost of the project easily by referring to the SRS document and that it contains all the information required to plan the project. Maintenance engineers. The SRS document helps the maintenance engineers to understand the functionalities supported by the system. Why spend time and resource to develop an SRS document? A well-formulated SRS document finds a variety of usage other than the primary intended usage as a basis for starting the software development work. In the following subsection, we identify the important uses of a well-formulated SRS documents. Forms an agreement between the customers and the developers. A good SRS document sets the stage for the customer to form their expectation about the software and the developers about what is expected from the software. Reduces future reworks. The process of preparation of the SRS document forces the stakeholders to rigorously think about all of the requirements before design and development get underway. Provides a basis for estimating costs and schedules. Project managers usually estimate the size of the software from an analysis of the SRS documents. Provides a baseline for validation and verification. The SRS document provides a baseline against which compliance of the development software can be checked. Facilitates future extensions. The SRS document usually serves as a basis for planning future enhancements. Characteristics of good SRS documents. The skill of writing a good SRS document usually comes from the experience gained from writing SRS documents for many projects. Concise. The SRS documents should be concise and at the same time unambiguous, consistent and complete. Implementation independent. The SRS should be free of design and implementation decision unless those decisions reflect actual requirements. Traceable. It should be possible to trace a specific requirement to the design elements that implements it and vice versa. Modifiable. Customer frequently change the requirements during the software development due to the variety of reasons. Therefore, in practice, the SRS documents undergo several revisions during software development. Also, an SRS document is often modified after the project completes to accommodate future enhancements and evolution. To cope up with the requirements changes, the SRS document should be easily modifiable. Identification of response to understand events. The SRS document should discuss the system responses to various undesired events and exceptional conditions that may arise. Verifiable. All requirements of a system as documented in the SRS document should be verifiable. Attributes of bad SRS documents. SRS documents written by novices, that is, inexperienced persons, frequently suffer from a variety of problems. The most damaging problems are incompleteness, ambiguity, and contradictions. There are many other types of problems that a specification document might suffer from. By knowing these problems, one can try to avoid them while writing an SRS document. Some of the important categories of problems that many SRS documents suffer from are as follows. Forward references. One should not refer to aspects that are discussed much later in the SRS document. Forward referencing seriously reduces readability of the specification. Wishful thinking. This type of problems concern description of aspects which would be difficult to implement. Noise. The term noise refers to the presence of material not directly relevant to the software development process. For example, in the register customer function, suppose the analyst writes that customer registration department is manned by clerks who reports for work between 8 a.m. and 5 p.m. 7 days a week. This information can be called noise as it would hardly be of any use to the software developers and would unnecessarily clutter the SRS document. Formal specification methods. In this video, we are going to see about formal specification methods. A formal technique is a mathematical method to specify a hardware and software system. To verify whether a specification is reliable, to verify that an implementation satisfies its specification, and to prove properties of a system without necessarily running the system, etc. The mathematical basis of a formal method is provided by its specification language. The set SYN is called the syntactic domain. The set SEM is called the semantic domain, and the relation SAT is called the satisfaction relation. For a given specification SYN and model of a system SEM, if SAT of sys SEM, then SYN is said to be the specification of SEM and SEM is said to be the specification of SYN. The generally accepted paradigm for system development is through a hierarchy of abstractions. Each stage in this hierarchy is an implementation of its preceding stage and a specification of the succeeding stage. The different stages in this system development activity are requirement specification, functional design, architectural design, detailed design, coding, implementation, etc. In general, formal techniques can be used at every stage of the system development activity to verify that the output of one stage conforms to the output of the previous stage. Syntactic domains. The syntactic domain of a formal specification language consists of an alphabet of symbols and a set of formation rules to construct well-formed formulas from the alphabet. The well-formed formulas are used to specify a system. Semantic domains. Formal techniques can have considerably different semantic domains. Abstract data type specification languages are used to specify algebras, theories, and programs. Programming languages are used to specify functions from input to output values. Concurrent and distribution system specification languages are used to specify state sequence, event sequence, state transition sequences, synchronization trees, parallel orders, state machines, etc. Satisfaction relation. Given the model of a system, it is important to determine whether an element of the semantic domain satisfies the specifications. This satisfaction is determined by using a homomorphism known as semantic abstraction function. The semantic abstraction function maps the elements of the semantic domain into equivalent classes. There can be different specifications describing different aspects of a system model, possibly using different specification languages. Some of these specifications describe the system's behavior and the others describe the system's structure. Merits and demerits of formal specification methods. In this video, we are going to see about merits and demerits of formal specification methods. Merits of formal specification methods. In addition to facilitate precise formulation of specifications, formal methods possess several positive features, some of which are discussed as follows. Formal specifications encourage rigor. It is often the case that the process of construction of a rigorous specification is more important than the formal specification itself. Formal methods usually have a well-founded mathematical basis. Thus, formal specifications are only more precise, but also mathematically sound and can be used to reason about the properties of a specification and to rigorously prove that an implementation satisfies its specifications. Formal methods have well-defined semantics. Therefore, ambiguity in specifications is automatically avoided when one formally specifies a system. The mathematical basis of the formal methods makes it possible for automating the analysis of specifications. Formal specifications can be executed to obtain immediate feedback on the features of the specified system. Demerits of formal specification methods. It is clear that formal methods provide mathematically sound frameworks within which large complex system can be specified, developed, and verified in a systematic rather than in an ad hoc manner. However, formal methods suffer from several shortcomings, some of which are as following. Formal methods are difficult to learn and use. The basic incompleteness results of first-order logic suggest that it is impossible to check absolute correctness of systems using theorem-proving techniques. Formal techniques are not able to handle complex problems. This shortcoming results from the fact that even moderately complicated problems blow up the complexity of formal specification and their analysis. Specification tools. In this video, we are going to see about specification tools. Software specification tools, software requirement tools, software design tools, software construction tools, software testing tools, software maintenance tools, software quality tools, software configuration management tools, software engineering management tools, infrastructure support tools, software requirement tools. Tools for dealing with software requirements have been partitioned into two topics: modeling and traceability. Tools used for eliciting, recording, analyzing, and validating software requirements belongs to requirement modeling. Requirements traceability tools are becoming increasingly important as the complexity of software systems grow, and since traceability tools are relevant also in other lifecycle phases, they have been separated from the other tools for requirement. Software design tools. There is a variety of such tools, with much of this variety being a consequence of the diversity of design notations and methods. While this variety of tools exists, no compelling partitions for this design tools were found. Software construction tools. Software construction tools are concerned with the production and translation of the program representation that is sufficiently detailed and explicit to enable machine execution. Program editors. Program editors are tools for creation and modification of programs. These tools can be general-purpose text or document editors, or they can be specialized for a target language. Editing refers to human-controlled development tools. Compilers and code generators. Traditionally, compilers have been non-interactive translators of source code, but there has been a trend to integrate compilers and program editors to provide integrated programming environments. Interpreters. Interpreters provide software execution through emulation. They can support software construction activities by providing a more controllable and observable environment for program execution. Debuggers. Debugging tools have been made a separate topic since they support the construction process but are different from program editors or compilers. Software testing tools. Testing tools are categorized according to where in the testing process they are used. Test generators. Test generators assist the development of test cases. Test execution frameworks. Test execution frameworks enable the execution of test cases in a controlled environment where the behavior of the object under test is observed. Test evaluation tools. Test evaluation tools support the assessment of the results of test execution, helping to determine whether the observed behavior conforms to the expected behavior. Test management tools. Test management tools provide support for managing all aspects of the testing process. Software maintenance tools. Software maintenance is often presented as additional iterations of the development lifecycle and consequently makes use of tools for all other phases. This category encompasses tools that have particular importance in software maintenance where an existing system is being modified. Two categories are identified: comprehension tools and re-engineering tools. Comprehension tools. These tools assist human comprehension of programs. Examples include visualization tools such as animators and program slicers. Re-engineering tools. Re-engineering tools allow the translation of a program to a new programming language or a database to a new format. Reverse engineering tools assist the process by working backwards from an existing product to create abstract artifacts such as design and specification descriptions, which then can be transformed to generate a new product from an old one. Software quality tools. Inspection tools. This topic covers tools to support reviews and inspections. Static analysis tools. This topic deals with tools that analyze software artifacts such as syntactic and semantic analyzers and data, control flow and dependency analysis. Such tools are intended for checking software artifacts for conformance or for verifying desired properties. Software configuration management tools. Tools for configuration management have been categorized as related to tracking issues associated with a particular software product, management of multiple versions of a product, or to managing the task of software release and build. Software engineering management tools. Management tools are subdivided into three categories: project planning and tracking, risk management, and measurement. Infrastructure support tools. These tools provide interpersonal communication, information retrieval, and system administration and support. These tools such as email, databases, web browsers, and file backup tools are generally neither specific to a particular lifecycle stage nor to a particular development method. Requirement validation. In this video, we are going to see about requirement validation. Requirement validation is a process in which it is checked that whether the gathered requirements represent the same system that customer really wants. In requirement validation, the requirement errors are fixed. Requirements error costs are high, so validation is very important. Fixing a requirements error after delivery may cost up to 100 times the cost of fixing an implementation error. Requirement checking can be done in the following manner. Validity. Does the system provide the function which is best support the customer needs? Consistency. Are there any requirements conflicts? Completeness. Are all functions required by the customer included? Realism. Can the requirements be implemented according to budget and technology? Verifiability. Can the requirements be checked? Requirements reviews. Requirements review is a systematic manual analysis of the requirements. The requirement review should be taken only after formulation of requirement definition, and both the customer and contractor staff should be involved in reviews. Reviews may be formal with complete documents or informal. Good communications should take place between developers, customers, and users. Such a healthy communication helps to resolve problems at an early stage. Prototyping. The requirements can be checked using executable model of system. Test case generation. In this technique, the various tests are developed for requirements. The requirements check can be carried out with verifiability. Is the requirement realistically testable? Comprehensibility. Is the requirement properly understood? Traceability. Is the origin of the requirement clearly stated? Adaptability. Can the requirement be changed without a large impact on their requirements? Requirement management. In this video, we are going to see about requirement management. Definition. Requirements management is the process of managing changing requirements during the requirements engineering process and system development. Why requirements get changed? Requirements are always incomplete and inconsistent. New requirements occur during the process as business needs change and a better understanding of the system is developed. System customers may specify the requirements from business perspective that can conflict with end user requirements. During the development of the system, its business and the technical environment may get changed. Requirement management process. Following things should be planned during requirement process. Traceability is concerned with relationship between requirement sources and their system design. Various types of traceability are source traceability, requirements traceability, design traceability, source traceability. These are basically the links from requirement to stakeholders who propose these requirements. Requirements traceability. These are the links between dependent requirements, design traceability. These are the links from requirements to design, requirement storage, change management, traceability management. Traceability information is typically represented by a data structure traceability matrix. If one requirement is dependent upon the other requirement, then in that row column, cell D is mentioned, and if there is a weak relationship between the requirements, then corresponding entry can be denoted by R. For example, for mentioning the traceability of small systems, usually the traceability matrix is maintained. Requirement analysis. In this video, we are going to see about requirement analysis. Requirements analysis is a software engineering task that bridges the gap between system-level software allocation and software design. It enables the system engineer to specify software function and performance, indicate the software's interface with other system elements, and establish constraints that software must meet. Requirement analysis, that is analysis, allows the software engineer to the software allocation and build models of the data, functional and behavior domains that will be treated by software. Finally, the requirement specification provides the developer and the customer with the means to assess quality once software is built. Requirement analysis is divided into 5 areas: problem recognition, evaluation and synthesis, modeling, specification, review. Problem recognition. Initially, the system analyst studies specification of the software and project plan, and the analyst must establish contact with management and technical staff of the user or customer organization and software development organization. The project manager can serve as a coordinator for establishment of communication paths. The goal of the analysis is to reorganize the basic problem element which is perceived by the user or customer. Evaluation and synthesis. Problem evaluation and solution synthesis are the next major area of effort for analysis. The analyst must evaluate the flow and content of information, then define and expand all software function, understand software behavior in the context of event of the effort system, establish system interface characteristics, and uncover design constraints. Each of these tasks serves to describe the problem so that the overall approach or solution may be synthesized. Evaluating the problems and desired information with the input and output, and the analyst begins to synthesize one or more solutions. Throughout the evaluation and solution synthesis, the analyst's primary focus is on what or how does the system produce data and consume, what functions must the system perform, what interfaces are defined, and what constraints are applied. Modeling. During the evaluation and solution synthesis activities, the analyst creates models of the system in an effort to better understand data and control flow, function processing, and behavior operation. The model serves the foundation for software design and the basic for the creation of a specification for the software. Requirement specification. After making the module, analyst makes a plan and schedule for development. The information gathered during the system study was analyzed to determine the requirement specifications. Based on the issues governing the system, requirements in non-technical terms are formulated. We need to develop a rough prototype to check the basic functionality of the software. If the major modules are not working properly, then the software might not satisfy the user. Interaction between the operator and system must be fast and reliable. Difference between data and information. In this video, we are going to see about difference between data and information. Data, information. Data consists of unprocessed raw facts and figures. Information is the processed form of data. Data is used as input in the computer. Information is the output of the computer. It has no contextual meaning. Information is a meaning. It has just numbers and text. Data with exact meaning. Data is used rarely. Processed data and organized context. Data is an independent entity. Information is interpreted data. Data is not used in decision making. Information is very important for decision making. Data is normally huge in its volume. Information is normally short in volume. Data is an unprocessed information. Information is a collection of processed data. Data is not significant to a business and of itself. Information is significant to a business and of itself. For example, 23 is significant for business, but age 23 is significant for a business like music. Data is an atomic level pieces of information. Information is a collection of data. For example, age and 23 collected together to form information. Data is not meaningful. Information depends on data. Data is captured and thereby unrelated to source. Information retains and conveys such relationship with source. Data is the assets of organization and is not available to people for sale. Information is normally available to people for sale. The figure explains the comparison between data and information. ERD, Entity Relationship Diagram. In this video, we are going to see about ERD, that is Entity Relationship Diagram. Another tool for requirement analysis is the Entity Relationship Diagram, often called as ER diagram. It is a detailed logical representation of the data for an organization and uses three main constructs, that is, data entities, relationships, and their associated attributes. Entities. An entity is a fundamental thing of an organization about which data may be maintained. An entity has its own identity, which distinguishes it from each entity. An entity type is the description of all entities to which a common definition and common relationships and attributes apply. Consider a university that offers both regular and distance education programs. Program and student are both entity types in this example. Regular and distance education are entities of program, whereas national and international are entities of student. We use capital letters in naming an entity type, and in an ER diagram, the name is placed inside a rectangle representing that entity. Relationship. A relationship is the reason for associating two entity types. These relationships are sometimes called binary relationship because they involve two entity types. Some forms of data model allow more than two entity types to be associated. A student is registered for a program. Relationships are represented by diamond notation in the ER diagram. We consider another example in which a teaching department of a university is interested in tracking which subjects each of its students has completed. This leads to a relationship called completes between the student and subject entity types. As indicated by the arrows, this is a many-to-many relationship. Degree of relationship. The degree of a relationship is the number of entity types that participate in that relationship. Thus, relationship completes is of degree 2 since there are two entity types, student and subject. The three most common relationships in ER models are unary, that is degree 1, binary, that is degree 2, and ternary, that is degree 3. Unary relationship. Unary relationship is also called recursive relationship. It is a relationship between the instances of one entity type. An instance is a single occurrence of an entity type. For example, there is one student entity type in universities, but there may be hundreds of instances of this entity type in the database. Is married to is one-to-one relationship between instances of the person entity type. That is, each person may be currently married to one other person. In the second example, is friend of is one-to-many relationships between instances of the student entity type. Binary relationship. Binary relationship is a relationship between instances of two entity types and is the most common type of relationship encountered in ER diagrams. The first, that is one-to-one, indicates that a student is assigned a student ID and each student ID is assigned to a student. The second, one-to-many, indicates that a program may have many students and each student belongs to only one program. The third, many-to-many, shows that a student may register for more than one subject and that each subject may have many student registrants. Ternary relationships. Ternary relationship is a simultaneous relationship amongst instances of three entity types. The relationship may have provides the association of three entities, that is teacher, student, and subject. All three entities are many-to-many participants. There may be one or many participants in a ternary relationship. In general, n entities can be related by the same relationship and is known as n-array relationship. Cardinalities and optionality. Suppose that there are two entity types A and B that are connected by a relationship. The cardinality of a relationship is the number of instances of entity B that can be associated with each instance of entity A. Consider the example: a student may register for many subjects. The minimum cardinality of a relationship is the minimum number of instances of entity B that may be associated with each instance of entity A. If minimum number of students available for a subject is 0, we say that a subject is an optional participant in the register for a relationship. When the minimum cardinality of a relationship is 1, then we say entity B is a mandatory participant in the relationship. The maximum cardinality is the maximum number of instances. In our example, maximum is many. The modified ER diagram, the 0 through the line near the subject entity means a minimum cardinality of 0, while the crow's foot notation means a many maximum cardinality. Cardinality of relationships. Cardinality of relationships can be used to identify relationships between entity types. Attributes. Each entity type has a set of attributes associated with it. An attribute is a property or characteristic of an entity that is interest to the organization. Following are some typical entity types and associated attributes. Student, student ID, student name, address, phone number. Employee, employee ID, employee name, address. We can use an initial capital letter followed by lowercase letters and nouns in naming an attribute. In ER diagram, we can visually represent an attribute by placing its name as an ellipse with a line connecting it to the associated entity. The diagrammatic representation of attributes. Candidate keys and identifier. Every entity type must have an attribute or set of attributes that distinguishes one instance from other instances of the same type. A candidate key is an attribute or combination of attributes that uniquely identifies each instance of an entity type. A candidate key for a student entity type might be student ID. Some entities may have more than one candidate key. One candidate key for employee is employee ID, a second is a combination of employee name and address. If there is more than one candidate, the designer must choose one of the candidate keys as the identifier. An identifier is a candidate key that has been selected to be used as the unique characteristics for an entity type. The diagrammatic representation of identifier. The representation for a student entity type using ER notation. Using entity relationship diagram to represent data is still an important technique today. The data flow diagram and the ER diagram each highlight a different aspect of the same system. As a consequence, there are one-to-one correspondences that must be checked to ensure that an ER diagram and a data flow diagram are consistent over all applications. This suggests that it is desirable to use both methods such that we can view the logical issues from the two perspectives generated by these approaches. DFD, Data Flow Diagram. In this video, we are going to see about DFD, Data Flow Diagram. Data flow diagram DFD. A data flow diagram DFD is a tool that depicts the flow of data through a system and the work or processing performed by that system. Synonyms include bubble chart, transformation graph, and process model. A DFD has 4 types of symbols: external entity, process, data flow, data store. External entity. An external entity is a source or a destination of data. Process. A process transforms data from one form to another. This transformation may be logical or physical. Data flow. A data flow is the path over which the data flows as it travels through the system. Data store. A data store represents a place in the DFD where there is a logical requirement for holding data from transaction to transaction. A DFD is used to describe what data flows rather than how it flows. The concern is understanding the transformation that are required to convert the input to output. It is independent of hardware, software, data structure, and file organization. DFDs are drawn at various levels of abstraction. The entire system is represented by the level 0 DFD, which gives the system boundaries and its interactions with the environment. Here, the entire system is depicted as a single process. All its interactions with external entities and the input and the output data flows are depicted. The level 0 DFD is also called the top level DFD or the context diagram. Further details of the system are shown in lower level DFDs. In this way, the process represented as a single process in the level 0 may get expanded as the number of processes in the level 1 DFD with the data flows between them depicted and the data stores also depicted. A level 1 DFD process may again be expanded into its constituent process in a level 2 DFD and so on. Expanding the information into a lower level DFD is also called exploding in DFD. In order to be able to record more information in a DFD, many analysts use the newer symbol set for a DFD. Example of a data flow diagram. Certain rules while drawing DFDs are: all data flows must contain data. If 2 or more documents travel together, they should be shown as one data flow. All data flows must begin from end at process, as a data flow either initiates a process or is the result of a process. There cannot be a data flow directly from one data store to another. In physical DFDs, a process may be required to show routing or forwarding of data that may not change the data. Control flow diagram. In this video, we are going to see about control flow diagram. There are certain applications which are event-driven rather than being data-driven. They produce control information rather than producing data, maybe report displays. Such applications can be modeled with a control information along with data flow modeling. A graphical model used to represent the control information along with the data flow model is called control flow model. The following guideline is used while drawing the control flow diagrams. List all the sensors that can be read. List all the interrupt conditions. List all the switches actuated by the operator. Use noun-verb passing technique to identify the control information. Describe behavior of the system by identifying the states. Define the transition between the states. Avoid common errors while specifying the control. Rules for designing CFD. No process can have only outputs or only inputs. The process must have both outputs and inputs. The verb phrases in the problem description can be identified as process in the system. There should not be a direct flow between data stores and external entity. This flow should go through a process. Data store labels should be noun phrases from problem description. No data should move directly between external entities. The data flow should go through a process. Generally, source and sink labels are noun phrases. Interactions between external entities is outside scope of the system and therefore not represented in DFD. Data flow from process to a data store is for updation, insertion, deletion. Data flow from data store to process is for retrieving or using the information. Data flow labels are noun phrase from problem description. Control and process specification. In this video, we are going to see about control and process specification. Each system continuously changes its state as information flows through it. This information flows through the system, initiates variety of processes in the system that changes the system's state from one state to another. This dynamic behavior of the system under various control signals can be seen from the other point of view with the help of state transition diagrams for state and control specification. Each event in the form of input or changes in some control variables influences the system and initiates appropriate actions to take care of that event. Being a large information system, there is an enormous number of events taking place. The system must be capable of handling such events. To explain behavioral description, states of the system are broadly classified into following 5 categories. State 1, State 2, State 3, State 4, State 5, State 1. This handles all possible states that are generated after accepting input from the user of the software. State 2. This contains the state generated due to data addition or modification. State 3. This is a query processing state. State 4. This handles the report generation for internal as well as external use of the system. State 5. This is a pure search state to build and update source list and prospective donors list with the help of web search. Data dictionary. In this video, we are going to see about data dictionary. Definition. The data dictionary can be defined as an organized collection of all the data elements of the system with precise and rigorous definitions so that the user and system analyst will have a common understanding of inputs, outputs, components of stores, and intermediate calculations. The data models are less detailed, hence there is a need for data dictionary. Data dictionaries are lists of all of the names used in the system models. Descriptions of the entities, relationships, and attributes are also included in data dictionary. Typically, the data dictionaries are implemented as a part of structured analysis and design tool. The data dictionary stores following type of information. Table shows the information of data dictionary. The notations used in data dictionary are shown in this table. For example, consider some reservation system. The data item passenger can be entered in the data dictionary as shown in this figure. The data dictionary defines the data items unambiguously. One can give the detailed description of data items using data dictionary. For large computer-based system, the size of data dictionary is very huge. It is also complex to maintain such a data dictionary manually. Hence, automated, that is CASE case tools can be used to maintain the data dictionary. Advantages. Data dictionaries support name management and avoid duplication. It is a store of organizational knowledge linking analysis, design, and implementation. IEEE SRS template format. In this video, we are going to see about IEEE SRS template format. Introduction, purpose, scope, definitions, acronyms and abbreviations, references, overview. Number 2, overall description, product perspective, system interfaces, user interfaces, hardware interfaces, software interfaces, communication interfaces, memory constraints, operations, site adaptation requirements, product functions, user characteristics, constraints, assumptions and dependencies, apportioning of requirements. Number 3, specific requirements, external interface requirements, user interfaces, hardware interfaces, software interfaces, communication interfaces. Specific requirements, sequence diagrams, classes for classification of specific requirements, performance requirements, design constraints, software system attributes, reliability, availability, security, maintainability, other requirements, supporting information, table of contents and index, appendixes.